Good morning, students. Welcome back to our lecture series on remote sensing, and welcome back to our topic on resolution. Previously, we have talked about spectral and spatial resolution. Now, also, just a quick recall from the previous topics, lectures. So, basically, resolution is used to represent resolving power, which includes not only the capability of identifying the presence of two objects, but also their properties. So in qualitative term, the resolution is the amount of details that can be observed in an image. And we have talked about that there are about four types of resolution, like spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. In this lecture, this particular video, we are going to focus ourselves on radiometric resolution. Okay? So what does the term radiometric resolution represent? So first of all, before beginning anything, when we talk about resolution, we are actually not talking about the satellite. We are talking about the sensor characteristic. So resolution is a characteristic of a sensor, and we are talking about different type of characteristics. So the resolution of a sensor is used in a satellite system. It is also applicable to any other simple system which you are using right now. For example, your mobile camera, our eyes itself, or any other handheld device or any other webcam from which you can actually capture the data. It could be also your temperature gun, the LSD gun which you are using right now for detection of temperature. Okay, so this all a different type of resolution are characteristics of the sensor which is used in equipment. And here we are specifically talking about the sensors, the resolution characteristic of a sensor which is used in a remote sensing satellite system. Okay. The example which I am going to discuss will also be related to the satellite images. Okay. So let us begin our today's topic on radiometric resolution. So radiometric resolution of a sensor is a measure of uh, how many gray levels a sensor can measure between pure black to pure white. Now when I say pure black, I mean when there is no reflectance, absolute no reflectance. And when I say pure white, it, it is totally white, that is full reflect. Okay, total opposite of no reflect. In other words, I can say that radiometric resolution represents the sensitivity of the sensor to the magnitude of the electromagnetic energy. Okay, a simple proper definition. It represents the sensitivity of the sensor to the magnitude of electromagnetic energy. Okay. The finer the radiometric resolution of a sensor is, the higher sensitivity, the more sensitive it is to detecting the small differences. Once again, keep noting that it is, I am saying, the small differences in reflected or emitted energy, or in other words, the system can measure more number of gray levels. Okay. One more thing is to be noted that radiometric resolution is measured in bits. So each bit records an exponent of power 2. So if you have again any confusion, I am repeating it, that the second point, which is much more important for understanding radiometric property of a sensor, that the finer the radiometric resolution of a sensor is, the more sensitive it is in detecting small differences in the image, in the reflected energy, or it could be emitted energy. Okay, so the finer, it would give you a more number of gray levels. The next table which I am showing you will help you in understanding the fourth point, that is how bit exponent to the power 2 is used here. So for example, if you are talking about 1 bit, it becomes 2 raised to 1 exponent to the power 2. of power. Okay. The maximum number of brightness level available depends on the number of bits used in representing the recorded energy. So if I say I have a sensor with radiometric resolution of 1 bit, I am saying that I have a number of levels, say 2 levels, that is black and white, or reflectors, full reflector. If I say I have 7-bit resolution of radiometric resolution sensor, it says 2 raised to 7, that is 128 levels of resolution. Energy can be recorded, of gray level can be explained. So here, this table actually shows the radiometric resolution and the corresponding brightness level available. Okay, for example, IRS 1A and 1B, which are 7-bit radiometric resolution, has 128 level. Landsat is 8-bit radiometric resolution, it has 256. NOAA and VAVHR has 11-bit of radiometric resolution and it has 2048 levels. So this particularly display means that the image data that is generally displayed in the range of gray tones. And actually, when you capture an image and the data has been processed, it is in gray form, a gray level. So here the black is represented by a digital number 0 and white is represented by the maximum value. For example, in 8-bit data, for an 8-bit data resolution which has 256 level, the white is represented by 255 number. Thus, if a sensor use from this table, we can say that if a sensor used 11 bits to record the data, there would be 2 raised to 11, that is 2048 digital value available, ranging from 0 to 2047. However, if only 8 bits were used, then only 8, 2 raised to 8, that is equal to 256 value, which ranges from 0 to 255, would be available. Thus, the radiometric resolution would be much less when compared to 8-bit and 11-bit. Image data, which are generally represented in gray tone with black representing 0, white representing 1. By comparing a 2-bit image with an 8-bit image, we can clearly see that there is a large difference in the level of details, which discriminate depending on the radiometry. In an 8-bit system, where black is measured 0, white is measured 255, the variation from black to white is scaled in 256 classes. Okay? Similarly, for 2048 level, it uses an 11-bit system, as shown in earlier figure. Okay? Now here a simple representation of different compared to this, and how the level has been divided, shown in figure. So you can clearly see that when it is a 1-bit, there is only one scale, 0 and 1. When it is 2-bit, there is three scales. When there is 8-bit, there are 255 scales, 256 levels. And when it's 10-bit, there are 1024 levels. One more thing you have to understand, that the finer the radiometric resolution, more the number of gray levels system can record, and hence more details can be captured in an image. Here a figure is showing a comparison between a 2-bit image with an 8-bit image. So 2-bit data is called a coarser resolution data, and 8-bit data is called the finer resolution data. Okay? From which a large difference of in the level of details. Once again, details. Even the spatial resolution is same, even the spectral resolution is same. If your radiometric resolution, the bits capture is different, you can clearly see that how the data, the details in the image is different. Okay. As the radiometric resolution increases, the degree of details and precision available will also increase. However, increase radiometric resolution will also increase the storage requirement of the data. So require higher storage requirements for high resolution, high radiometric resolution data. So in short, it means that the finer the resolution, the higher the storage required. Right? In an image, the energy received is recorded and represented using a digital number. Okay, in previous lecture, when I used the DN as a term, I mean digital number. So the DN in an image may vary from 0 to a maximum value depending on upon the number of the gray levels that the system can identify. By gray levels I mean the radiometric resolution. Thus, in addition to the energy received, the DN for a pixel varies with the radiometric resolution. For the same amount of energy received in a coarse resolution image, which could record a less number of energy level, a lower value is assigned to the pixel compared to a finer resolution image that could record a higher number of energy levels. Now it is explained with an example here. If you remember, for example, here I have shown an example. Suppose a remote sensing system with a radiometric resolution of 6 bit assigns a DN value of 28, 45, and 48 on 3 surfaces. Okay, 28, 45, and 48 on 3 surfaces. Then what would be the equivalent DN digital number for the same surfaces if the measurement were taken with a 3 bits? Okay, once again, this is a very simple and tricky example actually. That I have a remote sensing system with 6 bits of resolution and it measures the level DN number, that is digital number, at 3 surfaces. Okay, is 28, 45, and 48. What would be the equivalent DN in the 3 bit system? So here you can say that the DN recorded by a 3 bit system ranges from 0 to 7. That we know, compared to 6 bit system that ranges from 0 to 63. Okay. So this range is equivalent to 0 to 63 of a 3 6 bit system. So here you can see that a particular what we have done is nothing but here I have assigned 0 to 7, that is a 3 bit system, 0 1 2 3 4 5 6 7. Right? And in 6 bit system I have divided that 6 bit, that's the 0 to 63, in 8 different levels. Actually it is 7 because starting will be the same, ending will be the same. So I have divided the number between this 0 to 63 in 6 different equivalent numbers. Therefore, a DN of a 28 on a 6-bit system will be recorded as 3 in a 3-bit system. Okay, the nearest number 28 is 27, weighted 3. The second one is 45 and 48 will be 5. Now, a 6-bit system could record the difference in the energy level 45 and 47, whereas a 3-bit system will only record 5. See how a difference in bit could change the details in the image, and that's the reason why in this image here you have same color while there is a different of gray levels in this image. The same falls for colored image also. Okay, so whenever you see a grayscale image which can be converted to a colored image, which we'll see in the next topic when I'm going to show you about temporal resolution. So at that time you can see that how we are going to cover the area with a particular color. But when we talk about a radiometric resolution, the details of the information, you can see that the same level has been assigned at many regions, but when we see a finer data, you can see a minor difference in each and every. Now this type of information may be useful, may not be useful. It depends on your application. Okay? If your application requires low resolution radiometric resolution image, the coarser image is okay. the details of the information is not that much required, then it's okay. If you are taking of an image of a road, okay. But if you want to know where the pit is on the road, at that time you have to go for a finer resolution. So again, come back to this example. So therefore, when two images are to be compared, they must be of the same radiometric resolution. It has to be noted. Otherwise, you will of course get some differences, which you can't explain in detail. It would create a worst possible system. Okay, students. I hope you have enjoyed this lecture and quite understand the example which I want to show you. But if you are unable to understand the example, if you want more explanation, you can of course inform me on the group, or you can raise your query on the forum. So thank you for being patient. Thank you for listening to me. Goodbye. Happy learning.